3.5 is on page 244. It talks about the summary of curve sketching. This section is referred to in your next two semesters, 5B and 5C, 3 or 4 times. They teach you a new trick and they say, along with section 3.5, sketch the graph now. It says you need 8 things to really sketch a graph. Find the domain, we do that. Intercepts, definitely. Symmetry, if you wish. I really don't look for symmetry that often. Asymptotes, definitely. Increasing, decreasing, that's the first derivative test. And concave up, concave down, that's the second derivative test, along with the flexion point. And eventually you sketch. We start with something basic. So keep in mind, we knew few things about this graph from previous class, but there were things that we didn't label. Now we're going to label. Domain is already numbers, obviously, right? So we don't have to worry about that for polynomials. Intercepts. If I set x equal to 0, I'll get a 2. If I set the y equal to 0, let me see what happens. The only possible rational zeros are plus or minus 1, plus or minus 2. And if I try to figure out if 1 works, 1, nope, that doesn't work. Negative 1, nope. 2 will give 12 minus 8, nope, no. This is irrational. It doesn't work in that case. Alright, so this is what I know so far. I know on the graph, so far I know that, I need to stretch it. Okay. I know that the graph passes through the point 0, 2. Well, first derivative test. If I take y prime, that is 6x minus 3x squared. Where does that equal to 0? That's when 3x into 2 minus x equal to 0, right? Now, I have critical numbers of x equals 0 and x equal 2. I'm going to do a nice trick. I am going to come back and do the testing where the derivative is increasing, decreasing, but I'm going to jump to the second derivative to elaborate what we learned last time. The second derivative would be 6 minus 6x equal to 0. That's when x equal 1. Look what happens if I tested the second derivative. A point to the left of 1, say 0. That's positive, concaving up. And a point to the right of 1, say 2. 6 minus 12 is negative, concaving down. Do you see that zeros right there? That makes it a minimum. So I know that we have a local minimum at 0, 2. If this is a minimum, then it looks like that. And do you see that 2 is really in there? Isn't that a maximum? I know that we have a local maximum at the point 2. And if I plug 2 in, what do I get? 2 plus 12 minus 8. That would be 14 minus 8, a 6. Oh boy. Okay. Let's go this way. Actually, let's go this way. 1, 2, 1, 2, 3, 4, 5, 6. And let me shrink that down a bit. Let's make that 0, 2. There we go. That's a minimum. That's a maximum. I could come here and say, well, let's test 0, let's test 2, right? And I could say, well, if I pick negative 1, that's a negative, that's a positive, so the function is decreasing. Between 0 and 2, say 1, 3, 2 minus 1 is 1, that's positive. And to the right of 2, if I pick 3, that's positive, 2 minus 3 is negative. So I knew already that the function was decreasing from negative infinity to 0, union with 2 to infinity, because that's what a maximum looked like. And f is increasing from 0 to 2. And I already labeled the maximum minimum. I know there's an inflection point at 1, and if I plug 1 in, what do I get? If I put a 1 in there, I'll get 2 plus 3, that's 5. 5 minus 1 is 4. 1, 1, 2, that's 1, 2, 3, 4. That's an inflection point. Well, let's see. If I want to map concaving up from negative infinity to 1. That's concaving up. And if I want to map concaving down from 1 to infinity, from 1 to infinity, that will be concaving down. And that's satisfying all the cases. The next problem, I'm going to put everything in a better order, but there it is. The next problem, I want to tackle this. Now, we know what this graph looked like. We don't need calculus for that, but we never labeled concavity. So, if I glance at this, I already know the domain. X cannot equal plus or minus 2, and I know on the graph those are vertical asymptotes. Those are lines you can get very close to, but you can never reach. Intercepts. If I let x equal 0, I'll get negative 1/4. That's good. 0, negative 1/4. The graph passes through this. Right? Now, I do know that there's a horizontal asymptote of y equals 0 as well. So a combination of what you know along with calculus will go a long way. Well, if I want to find the first derivative test, can't I think of this as x squared minus 4 to the negative 1? So if I take a derivative of this to figure out where function is increasing and decreasing, y prime would be negative x squared minus 4 to the negative 2 times 2x. That would be negative 2x over x squared minus 4 squared. Where does y prime equal 0? Where does y prime not exist? Third time will be fine. So a fraction equals 0 if the top equals 0, denominator equal plus or minus 2. So if I look at 0, 2, and negative 2, this is y prime, this is y. If I pick negative 3, the denominator is always positive. Negative 2 times negative 3 is a positive increasing. And negative 1, that's still increasing. If I pick 1, negative 2 times 1 is negative, that's decreasing. And if I pick 3, that's decreasing. So it seems we have f is increasing from negative infinity to negative 2, union with negative 2 to 0, right? And f is decreasing from 0 to 2, union with 2 to infinity. And we have a local max at 0, negative 1/4. It seems this is a maximum, which means the graph looks like this. If I take the second derivative, I'm going to take the derivative of this. Y double prime. Derivative of the top is a negative 2 times the bottom, minus the top times derivative of the denominator. I'm going to shift this to the right a bit. Times derivative of the denominator. The denominator, you will have to bring the power down, subtract 1 from the power, times 2x, all over the denominator squared. Y double prime is going to equal, and I'm going to shift this a bit to the left. It seems I always go to the right a bit more than I should. There we go. Yeah, should have plenty of room. And if I factor out the negative 2 and x squared minus 4 squared, I would have left, if I take the negative 2 into that, not squared, to the 1. I'll take care of that in a minute. Out of this, there'll be x squared minus 4 left. Done. I took the negative, I took the 2, and I took that. Negative 2x times 2x is a minus 4x squared. I am left with a negative 2 and 2. And what is that? Isn't that negative 3x squared minus 4? Let me just double check my work really quick. Yeah, everything's matching. So if I would go ahead right now, the top, this can never equal 0. And since they're all negative, if I multiply those out, that's all positive. So my only points to test are -2 and +2, y double prime and y. The top is always positive, right? If I pick -3, 9 minus 3 is 9 minus 4 is positive. If I pick 0, that will be negative and a positive. So concave up, concave down, concave up. So we know that f is concaving up from -infinity to -2, union with 2 to infinity. F is concaving down from -2 to 2. We have, well, those are not inflection points. We can't test those. So, concaving up, we know the graph must look like that. Concaving down, passing through that, there it is, and concaving up, there it is. If it was concaving down, I would have did this. That pretty much tells you how the shape looked like. The graph looks like this. And there it is. Case 6 is the only problem I could do in about 4 minutes, so I have to choose. I really want to do different problems, but in the next video I still have some for you. So I look at this problem, domain all real numbers, intercepts. Well, this is x into x to the 4th minus 5. So if x equals 0, y equals 0. But if y equals 0, I'll get 0 is already there. I'll get the 4th root of 5 and -4th root of 5. So far I have these values on the graph. The graph must pass through the origin. And 4th root of 5 is a bit bigger than 1 and a bit smaller than 1. If I take y prime, that is 5x to the 4th minus 5 equal to 0. That's when x to the 4th minus 1 equals 0. That's x equal plus or minus 1. So if I test 1 and -1, there's y prime, there's y. If I pick a value to the left, say -2, -2 in there will give a positive. A 0 in there will give a negative and a positive. So I know I have a maximum at -1. And if I plug that in, -4, -1, yep. And I have a local minimum at 1. If I put a 1 in there, -4. -1, 4, 1, 2, 3, 1, 2, 3, 4. That is a maximum. Maximums look like this. And at 1, -4. Right? Just to be able to finish, I'm going to tackle the second derivative. That is 20x cubed equal to 0 when x equals 0. So 0 is the only point I can worry about. If I pick -1, put it in there, that's a negative, concaving down. And if I put 1 in there, that's positive, concaving up. So the graph is concaving down from -infinity to 0. 0 is an inflection point, something like this. And the graph is concaving up from 0 to infinity, passing through that point and that point. And that's how the graph looked like. And of course, I do have time. I could say all of those now. F is increasing from -infinity to -1, union with 1 to infinity. F is decreasing from -1 to 1. F is concaving up from 0 to infinity. And F is concaving down from -infinity to 0. We do have an inflection point at the point 0, 0. And there it is. In the next video, I'll wrap this up. I'll see how many problems I can do. I'm hoping for 3. We'll see how that goes.